All right, so Melissa asked to do a couple points on a titration, and her specific question had to do with what happens to the volumes when you keep going along a titration. So I have a picture here. I'm going to try coloring it in and as we go and see if that helps visualize what's happening in the titration a little bit better. First thing that it's useful to do is figure out what type of titration you have. And so if I read the problem, I see that I have NaOH, which happens to be a strong base, and then I have HCl, which happens to be a strong acid. So this is a strong titration. And to figure out which one goes in the burette and which one goes in the flask, one of them is going to be added to the other. And you can see that the NaOH is added to the HCl. And so if it's going to be added, it will be added from the burette. And the burette generally holds your titrant. And so that means that the HCl must be in the flask, and that in the flask is our analyte. So I know that it's a strong acid, strong base, because the analyte goes first in our nomenclature. And so it's an HCl NaOH titration. Now it's not one of these points, right? I just have two here, and neither one of them is the equivalence point. But I know that the pH at the equivalence point is 7 because it's a strong acid, strong base titration. Doesn't matter the concentrations, doesn't matter the volumes of each it takes to get there. Once you get the same number of moles of acid as base present in solution, you're going to have a pH of 7 because this is a strong titration. Now the other thing that may be useful to write sometime around now is a balanced equation. And so I'm going to do mine in the same order as the notation. And so I'll put the strong acid first, which is HCl. Happens to be an aqueous solution. I'll put the strong base second. Every time you put an acid and base together, you're going to get a salt, which is aqueous, and you're going to get water, which is a liquid. Now note that I drew a pretty stupid looking equilibrium arrow. This is so product favored that there's no appreciable back reaction. And so that means my math can be simplified. Simple stoichiometry of 1-to-1 ratios and species that completely dissociate are going to be appropriate here. So for every mole of this that was there, 1 mole of that's going to disappear every time 1 mole of that is added. It's 1-to-1. There's no ice tables to worry about, etc., because they dissociate completely. Now, I know that I have about 50 milliliters of acid because that's what it says in the problem. Make the acid red just because acids are usually red in books, at least on the pH scale. It's kind of arbitrary. Red litmus paper does turn red when you put it in an acid, so that's the other reason we can do this. Okay? So I got 50 milliliters of analyte. Doesn't matter which point in my titration I am at, I'm going to have 50 milliliters of analyte all the time. That's not going to change. Now, let me get a different color pen here. For A, I'm going to add 25 milliliters of base to this flask. And so if I had 50 and I add 25, I'm going to be upwards of 75 milliliters right now. Okay, and that's the total volume in solution. So whatever concentration I come up with needs to take that 75 milliliters into account. So since it's strong acid, strong base, I can start by figuring out the moles of acid that are present. I'm going to do volume times molarity there. And I'm going to end up with a value of 1.0 times 10 to the minus 3. That's going to be moles of HCl. That's the moles of red liquid there. I'm going to do something similar for the moles of the base. Still volume times molarity. Here I'm going to get 3.75 times 10 to the minus 4 moles of base. 3.75. Now if I look at these numbers, the acid is in excess here, right? There are more moles of acid than there are base, so I can predict that my pH should be acidic. Since there's more moles of acid than base, I bet if I can get the hydronium ion concentration that I can go straight from that to pH, which is also a benefit of strong acid, strong base titrations. So I need to figure out the moles of acid that are left. And I can do that by subtracting the moles of acid initially present, which is 1 times 10 to the minus 3. And I can subtract the base that I added from that. This equation was given in the original strong acid, strong base videos. I need to put this over the total volume, which we conveniently already found to be 75 milliliters. If I figure that all of that out, do all of that math, I get 8.3 times 10 to the minus 3 molar H3O plus. And since this is a strong acid, I do not need a ice table. And I can just go 8.3 times 10 to the minus 3 molar. Negative log of that's going to give me the pH, which I get a value of 2.08. Now I quickly did the initial value as well. The initial pH was 1.7. Wasn't part of the question, but I just wanted to double check that my numbers made sense. It should be more acidic, but not too much more acidic because it's within the buffer region. And so I think a difference of 0.3 kind of fits that bill. So that would be the answer to A. Now in terms of B, we're gonna add another 15 milliliters. So right now we are at 75. If I add another 15 mils to it, this gives me, and let me do this way. This gives me a total value of 90 milliliters, which was actually the question. So yes, we started with 25. We're just adding to the same flask. So 25 and 15 would be 40. And you have to remember the 50 milliliters of acid that were there to begin with. So we're going to do the same kind of moles math. I'm not going to do the acid over because we did it right here. Again, the amount in red will not change throughout the entire titration. So if I had an initial amount of acid at some point, I still have that same initial amount of acid. Moles of base will change though, because it's still volume times molarity, and the molarity is the same, but the volume has changed now. So now I have 40 mils instead of the 25 I had before. And so I get 6.0 times 10 to the minus 4 moles of base. To get the pH, we do the same thing though. We take the moles of acid we had initially, 1.3 times 10 to the minus 4, and we take the moles of acid that would have reacted, which happens to be the same amount as the moles of base that we added, and we divide that by the total volume. That's not milliliters either. In liters. And I think we come up with 7.78 times 10 to the minus 3 molar H3O plus. And if we take the negative log of the hydronium ion concentration, which happens to be that, we get a value of 2.11. Now we're still within the buffer region, so we should go up, but we shouldn't go up by a ton. And that's what looks like happened here.